talk here tonight at this awesome IBM building. We are going to hear from Mark Hager from IBM this evening, and then we'll have our keynote Neil, as he likes to be known, and then we'll kick into a Q&A session, because I know that there were heaps of questions that people had at the end of Professor Casaubon's session. And this is all about being able to dive into the nuts and bolts of spiking neural networks tonight. So, yeah, I'm AI Joe on Twitter. Follow me and you will hear first about these meetups so that you get a chance to RSVP before they fill up. But without further ado, I will invite up Mark Baker, who's the General Manager of Digital and Channel. We are very lucky to have him here tonight. If any of you are sort of interested in, have some questions for your efforts integrating with IBM's cognitive services and stuff, then you can grab him tonight and get your questions answered. So please welcome him up.
I have a pretty loud voice, so I may not need this, but hey, first of all, welcome to IBM. It's our pleasure to be able to host you guys along tonight, and obviously a great venue to have you here. If anybody needs to know where the toilets are, just go back out to reception there, and the girls will direct you into the toilets just off the left in the main reception there. So from my perspective, I just wanted to do a quick intro and give you a couple of highlights on what we've been up to recently. So some of you may not be aware, but we held our big annual event a couple of weeks ago on the 1st of May it was. And we had quite a number of people across Australia and New Zealand in the thousands that came along to that. Obviously New Zealand wasn't thousands, but we had close to 700-800 people come along to that event. And we really did focus on that kind of quantum computing, security, AI, and cloud and blockchain. Those were kind of the main streams of what we talked about. We also had some really good keynote speakers along to that. And if you'd like to see any of the highlights of that, I would recommend that you go online and have a couple of looks at some of those highlights. One of them was Chris Hadfield, that was an astronaut, and he did a phenomenal presentation. I've actually personally been to probably hundreds of keynote presentations around the world, and he would rank in my top 3. So if you really want to see somebody that's pretty inspirational, and he actually related kind of a lot of the stuff that IBM are doing technology-wise into what they're doing in that kind of space exploration stuff. He did a great job of that. So have a look at that. I think he spoke for close on probably 45 minutes, so worthwhile. It's all up online, and plus a lot of the other keynotes that you can see there. In the next couple of weeks, we're involved in Tech Week. So Tech Week is a bunch of events, obviously across Auckland, Wellington and Christchurch. And the focus is very much around AI, and there's quite a lot of family-friendly events involved in that. There's a lot of robotic challenges, lights festivals, etc. So Tech Week is quite a week-long event that lots of tech companies are involved in. So again, have a look at that online. Joe will share all the links to that sort of stuff. And then finally, in New Zealand, the New Zealand AI organisation, which is essentially the business side of what you guys are all involved in, pretty much. So we're involved over June and July around 4 kind of events, which actually are paid events. They're about $100, $95 to attend, I think. And those are going to be held, 1st of June will be data wrangling. And then Friday, June the 15th is conversational interfaces, so that's about chatbots. Then the 13th of July is Reimagine Customer Experience, and then on the 27th, Capability and Strategy. So if you're interested in those, again, Joe will share the links to that, and it might be something worthwhile getting along to and getting involved in. So welcome along. I'll hand back to Joe and go from there. Thank you.
Can you put after hours air conditioning on, please, this time?
Oh yes, I'll go and sort that
out.
Thank
you. Short and sweet. Thank you very much. Yeah, and also I've got housekeeping. If there is an alarm, then please follow me calmly out of the building. And also just want to thank IBM for the pizza as well. They are the key sponsor. They make this possible to happen each month, so let's give them a round of applause as well. after Professor Castlebar's talk on neural networks last time, I came to work the next day and I was raving to Neil about it because I've had the privilege first part of this year to work with Neil for a few months on some things. And I was like, oh yes, but neural networks is so cool. And he's like, oh yeah, I built that. I'm like, come again? So by like 8 AM, I think, the day after the meetup, we had this meetup scheduled for a deep dive into it because there was a huge amount of interest in it. So that was a really cool happenstance. And I'd like to now welcome up Neil to speak to us.
Hello everyone. First of all, am I audible at the back?
Yep.
Good. Thanks, Jordan. I have heard from Jordan that Professor Castlebar has already given some introduction and some very top-level view of what spiking neural network is and what are the applications that are there and those kind of stuff. What I thought I would do is that I would go a bit into the implementation detail. I won't go too much into it because it can get quite deep in terms of like what all things you can do as you go deeper down the line. What I also thought would be really interesting to do is to essentially place spiking neural network in the current ecosystem of the AI and neural network, deep learning, these kinds of environments, or where spiking neural network fits. Is there any kind of similarities, dissimilarities with deep neural network, deep learning, those kind of stuff, and so on. And I would, so you often see me talking, trying to compare what I have seen in spiking neural networks and what I have seen in deep neural networks and where I find the differences and commonalities and those kind of stuff. Right, so the agenda is basically I have divided into 4 different parts, you can say. First, I would just ask 2 of the burning questions that you would essentially find is what is spiking neural network and what are the differences and are they same? Are spiking neural networks and deep neural networks same? Then I would go at the lowest level of a neural network, which is a neuron, and try to do a bottom-up approach of you have neurons and then you have a network of neurons and how do you build those kind of stuff, so the detailed stuff. Then I would do a kind of top-down approach, which is you have an AI problem, so you have data, you have a question to answer, and you want to develop an AI application, and how do you go about it in terms of spiking neural networks and what are the kind of similarities and dissimilarities to how you design things in deep neural networks also. And then I would give a kind of brief demonstration on one of the tools that we have developed at Kedri in AUT, which is the NewCube, which is one of the tools available for doing spiking neural network based applications. And then I will also give one examples of how one other group has used spiking neural networks to basically solve an MNIST dataset problem, which is a handwritten digit recognition problem. So, to get into the burning questions, first thing is what is spiking neural network? So, I see it as there are 4 different components which makes up a spiking neural network. It is considered to be a 3rd generation of neural networks, where a generation is generally assigned to a neuron rather than a network of neurons. So you have different kinds of neurons, where neurons can be like first generation neurons, second generation neuron, third generation neurons, and sometimes you can find this generations can be more of a marketing ploy rather than anything else. Right? I mean, I'm going to give a very honest opinion about any kind of neural network that I find. So, and the second thing is that these neurons that sits inside this network of neurons works within a spiking ecosystem. So the data that goes in and the data that comes out are generally binary in nature, or to be slightly extending it, you can think of it discrete. So you sit in a discrete mathematics environment rather than in a continuous mathematics environment. And people who know their mathematics will know that each has its own like advantage and disadvantage in terms of what you can do with it. Third thing is that spiking neural networks are typically recurrent. So when this is a property of the neural network rather than the neuron itself. So rather than the computational unit, you're talking about a network of neurons at this point in time. So recurrent means so within the same layer, the neuron can feed back to itself or feed back to other neurons within the same layer. And one other very important aspect is that these neurons are generally spatially arranged. So there is a spatial component that how you arrange neurons within a particular network. So there is a spatial component that is attached to it, and because of the flexibilities that are there in spiking neural networks, these spatial components become important and more flexible in that way. Not necessarily useful always, but there is a level of flexibility that it provides in what all things you can do with it. And the fourth important thing is that the spiking neurons are very biophysical in nature. So you can mimic the biophysical activities within human brain or any kind of cell that exists. So you can mimic with mathematical model, you go more towards biophysics than towards your simplistic like mathematics across the activations of the neuron. The second important thing is deep neural network versus spiking neural networks. I basically see it as apples and oranges because spiking is a property of a neuron, whereas deep is a property of the network, right? So depth is basically when you have like multiple layers of stuff, right? Whereas when you see spiking, you see, I actually really like this particular image because it kind of gives you kind of a holistic view of what are the different kinds of neural network that exist, where networks are generally defined by how deep it is and also what type of neuron it is. So you'll see that here there are so many different kinds of neuron that kind of exists. And to be really honest, I see neural networks not as a typical machine learning tool. I see it as a computational graph. You will see that if you read like a bit about how something like TensorFlow or PyTorch, those kind of things are developed, you'll see that they define neural networks as a computational graph, and then you basically choose what you want to do with it. For example, a computational graph that is generally termed as autoencoders can mimic the behavior of principal component analysis. So principal component analysis does not necessarily need to be a neural network part. It is a computational tool, but neural network has the ability to mimic the behavior of it, right? So like another example is something like support vector machine. A neural network can totally behave like a support vector machine just by specifying the loss function as a hinge loss function. So you kind of, instead of using your traditional binary cross entropy and those kind of stuff, you make use of hinge loss, and hinge loss makes it like maximize margin rather than maximize some sort of error or some sort of log loss, right? So that's typically your deep neural network, and in a way, spiking neural networks, from a holistic point of view, you can think of it as a computational graph where the neurons sits in this spiking environment, where all the data that goes in are spikes, all the data that comes out are spikes, right? So that's basically on it. And spiking is basically the property of the activation, as I told. And I will discuss a bit more on this at the very end. Now, I wanted to go into the lowest level of detail first, which is neurons, right? Which is so when you see neurons, you must have seen it many times, but your biological neuron, in a simple comparison of biological neuron versus a computational neuron, is that in a biological neuron, you basically have this dendrites which collects the input and pushes it through the soma, like where all the integration and stuff happens, and then you have axons where things are broadcasted. So the outputs are broadcasted. So if you compare it to a spiking neuron, any kind of neuron as such, so your X's are the inputs which are over here. W's are, you can think about it as the thickness of these like dendrites. So thicker are the like dendrons, more things flow, so more the weight, right? So you have weights which are the thickness of these dendrons, and then there is, so typically there is a summation operation where you do some sort of convolution and then do some sort of transformation, and your output is generated, right? I hope it's visible from outside. So
There's another screen back there.
oh, okay, that's good. Right. Now coming into the first and the second generation of neurons, so it's not the first and second generation of neural networks, but first and second generation of neurons. So historically, neural networks started with the perceptron and Vidrohoff, like those kind of rules, where the activation of the neuron, which is basically here, started with a very simplistic step function that you do the integration, and if it is, it goes beyond a threshold, it's 1. If it's less than the threshold, it's 0. That's kind of a threshold gated stuff. And then there was this idea that instead of gating it, we will do a linear stuff. So this was the gate, where that's the input and the output. So like beyond the threshold, you kind of get an output, and otherwise you don't. And then you can have a linear, stuff. So then what happened was that there was this problem of non-linearly separable problem. So there were certain problems where things were not separable with a straight line, right? And then what happened? Then came the second generation of neurons, which basically was could essentially non-linearly separate things. And as soon as you put multiple neurons together, which works together, means multiple of these non-linear lines gets formed, and you can solve like convex, like decision boundaries. You can create those kinds of things. Now finally to the spiking neuron. If you see spiking neuron, so apart from the first and the second generation neuron, which was kind of very static in nature, so you put in a static value as input, it does some sort of summation, transformation, gives an output, right? Spiking neurons started with the idea, spiking neurons actually, the development of spiking neurons started happening during the 60s. That was focused more towards the neurophysiology of stuff, whereas people started developing more general purpose stuff. So what spiking neuron added to your first and second generation of neuron was a temporal component to it, right? So, which later on, of course, GRU, like LSTM, those things can also do. But thing is, one added point that spiking neuron that added in was a temporal component. So you can input data where a data at a particular point is related to the data at the previous point. So any kind of sequence as such. So not necessarily needs to be time. And it also integrated memory into it. So which is also one of the properties of something like RNN or like LSTM, those kind of stuff. So it integrated memory. So when an output comes out of a neuron, it not only considers at this point in time what my input it also considers what has happened historically. So its activations are time dependent. So you had seen in the previous slide, these were the activations of the neuron, but just for the sake of showing you how complicated, it has gone. As soon as you moved into spiking neural network environment, the simplistic activation has become a more complex activation over here, and you can see a T, like attached to a particular variable, which basically is the activation. So like a time component gets attached to it, right? And one other property of spiking neuron is that there are many different spiking neurons mathematical models of the neurons, where just by changing the parameters you can mimic the behavior of certain kind of brain cell that exists. So there is a certain mathematical model where once you change the parameters, it starts behaving like a neocortical cell or kind of vision cell, right? So that's one aspect of things. And one other important thing to notice here is this plot, which is the amount of computation that you need to do essentially increases with the biological plausibility. So as the biological plausibility increases, and your thing starts becoming more and more kind of prohibitive. So this is good, this is poor, by the way, it's not the other way around. So this is good. And so there are different kinds of neurons you can kind of put into this domain. So I will very briefly demonstrate how you simulate one particular neuron, but before that I just wanted to introduce you to a library which you can also go back in your home, in your own time, you can experiment with it, which is Pine. It's on Python, because we all love Python. And this is a spiking neural network environment which sits on top of multiple simulators that already exists in the kind of research area. So there are Nest PCSim neuron, there are multiple these simulators that are written by specific groups, and what Pine came in as, they basically integrated all of them and gave an interface on top where you can choose a simulator at the bottom and run any kind of simulation as such, right? Okay, so now I will briefly move to right. Okay, so the exercise that I'm going to, oh, you can't see that.
I love when they're scaling.
Right, so what I would do is that we would choose a simulator, and then we'll try to simulate one neuron first, right, and see what it gives, right, in general. So to do it, what you need to do is that, right, so if, that's fine, that's fine.
Sorry about the lowdown tape.
That's fine. That's useful. Right, so what we will do is that we will be setting up make use of Brian as a simulator, and set up a simulator that simulates a neuron for 100 milliseconds, right? Where you can see we are setting up a simulator and saying that simulate a neuron for, we will see the 100 millisecond part, and simulate every 0.1 millisecond, right? So let's set it up, and now we'll create a single neuron of a particular type of, here you have a Hodgkin-Huxley type of neuron, which is basically one of the neocortical type of neuron that exists.
So what does that time step mean?
Time step means it will simulate at every 0.1 millisecond. So the simulation is going to go on for 100 milliseconds, and it's going to just going to inject current into it, so which is basically input, right? So you have a neuron, you are going to put in inputs, and it's just going to spike over time. So how it spikes is being driven by lot of different parameters, right? I will show you.
Is it a differential equation internally?
Yes, it is.
Okay.
It is. Everything in spiking neural network sits on top of differential equations, and then there are a lot of ways to basically approximate it, but underneath it is differential equation, right? So what I'm saying is that here is a particular kind of neuron I want to simulate one of them, and I want to inject a default current into it, right? Did I run it? One thing I just wanted to show is that if you see the number of parameters with which you can control the behavior of this neuron is extremely large. So there are 13 parameters with which you can control it. But that also means that those many parameters you need to do hyperparameter search at the end. So things from like becoming computation heavy or kind of loaded becomes parameter heavy. So flexibility leads to more parameterization of stuff, right? So I will simulate a neuron. So what I'm saying is that record the internal potential, which is basically the activation, the output of stuff, and I will just plot that thing. So now you see it plots out a graph. So it does for 100 milliseconds for like every 0.1 iteration of stuff, and it basically creates a variable called a membrane potential, which basically goes up, and these points are the points where the spikes has come out of the neuron when you injected random stuff into it.
Is this injecting something every 0.1 seconds?
Yes, so by default, there is a way to inject random currents here, right, to it, but I will show you how you can inject externally. So that's what we want at the end, right? We want to inject external data into it. That's good. And this is just the behavior of one of the neuron for just one default parameter setup, right? I will run a script where it simulates like at least 4 or 5 different kinds of neurons. So it just runs it, let it run. Okay, so now you see that there are, so this is what we call as an integrate and fire neuron. So an integrate and fire neuron, what it does is that it takes the inputs, integrates it. If it goes beyond a threshold, it just cuts it down. So that's the point of spike. So like over time, current is going in, it's becoming more and more excited, and at this point, there is a threshold which cuts it down, right? There are many other different kinds of neurons that exist where you see the behavior, the spiking behaviors are different.
So the threshold which is considered to be a spike, is
Yes.
that just a parameter?
Yeah, exactly.
And could it be below or above?
Exactly. Could be below.
Oh, I guess that's the same for real neurons.
Yeah.
Yeah.
Right, so now I will show you an example of how you can do external current injection. So we are same configuration. I am going to set up a simulator. I am setting up a single neuron of a particular type where I don't have an...
Sorry, Neil,
Yeah.
when you look a certain way, it's
Oh, is it?
I wonder if you just put it a little bit higher up.
Oh,
maybe
perfect.
that'll stop happening.
That sounds like digital interference.
Good?
I'll
Can you
remove
hear?
my phone as well, just in case.
Right. Oh, okay, you're
I think the system is as bad as it. Turn this up often.
right. Is it fine? Is it fine if I do it like this?
It's too bad.
Right. Okay. So I will simulate it without any current injection. One neuron of a particular type. I do a current injection and run it for 1,000 milliseconds, and I will plot it, and you will see that there's nothing, right? Because there's no current that has gone in. It has not gone excited, and now I inject current, and here is the injection of current of a particular type. I mean, you don't need to worry about it at this point, and you see that it will do stuff, right? Same thing, you can do a step current, which we can do, but let's not do that. I mean, I have this in Docker, by the way. If you want it, I can distribute it. I can send it. Right. That's good. Okay, so
Can you interpret that graph for us?
I would not try to interpret this part because this part has come up because of the differential equation and the biophysical nature of the stuff that defines this particular neuron. So essentially we have injected current to this particular neuron, and based on the internal parameters that we have set, it actually behaved like this. So right now, in this particular scenario, there is no kind of proper causal explanation of why you see this, right? It's just driven by the internal parameters. And if there was a biophysicist who would have stood right here, he would have interpreted it for that particular neuron. I mean, because that's how these things work. And you can already see that at the lowest level of stuff, how biophysical it is, not necessarily very data driven, but quite biophysical in terms of, I mean, like what you can do with it, and it provides a lot of flexibility in terms of how things spike and how data get generated and so on.
Quick question about that. Is there some kind of steady state that eventually happens, or is it always like that at the beginning?
No, because like there are ways, like it's called refractoriness. So there are ways with which you can control those things as well. So you can push things into a steady state just by controlling the parameters and like so on. So there are so many different ways you can set the parameters that can kind of makes it behave differently. I just wanted to show like.
How does it fill into the practical data, such as this?
What kind of data?
Practical.
Practical data.
I will come to
face recognition.
I will actually come to that.
Okay.
So I was just wanted to show you at the kind of deepest level what happens for you to do stuff on the top most level. That's like an application, and from where you go down, right?
Yeah, sorry, but I didn't understand the difference between this output and the previous ones.
Oh, so the only difference between this output and the previous one is that we injected a different kind of input to it, and it behaved differently over time, right? So you kind of have a different excitation input and it behaves differently. Right, so, okay, I will finish my talk on spiking neurons, which can get a bit involved in that way, but okay. Right. Now we have seen some neuron. Let's go into a population of neurons. Now we are actually interested at the neural network level. So a population of neuron. Now you kind of think about, instead of having one neuron, I can have 20 different neurons. What other things we have to do to make it a computational graph, right? So as I said, the first important thing that spiking neural network does in terms of building a network of neuron is assigns a spatial location to each neuron as such. So like a neuron is spatially arranged. So you will have 1,000 neurons. You can have it spatially arranged within a single line. So you can have kind of geometric like arrangement of stuff. So you can, it can be distributed like within a line. It can be distributed in like 2-dimensional grid, 3-dimensional grid. It can be distributed randomly within a particular shape, I don't know. Or you can have a custom location of neuron. One example is like this. Here the neurons are arranged as the shape of a brain. So there is a custom brain shaped network of neuron that is here. So I will not go into the fine code for that for now. That's the second aspect, is how do you connect them. One is the spatial arrangement, and what are the different ways of connecting the neurons, right? So in a way, like as soon as you come to the connection of neurons, you can think of it now as a directed acyclic graph, right? You have a graph consisting of neuron, and there are directed edges. To be like really specific, it is kind of an incomplete directed acyclic graph, where the neurons are not connected to all the neurons, but it's generally connected to the neighborhood. That's an important aspect of spiking neural network. It can mimic spatial behaviors just because it generally broadcasts or propagates its output in the immediate vicinity rather than everywhere else, right? It's you can think of it like in a convolutional neural network, how you kind of do parts of the like input goes into the next layer and parts goes into other layer, that kind of a stuff. but more spatially arranged. I will come into one later on into how spatially arranging things are useful, but we'll leave it for now. Some things that we need to understand, so like apart from connection, spiking neural network also allows to mimic different kind of synapses or connections. So typically, in a traditional or canonical neural network, synapses are just propagating the data into it, right? Now, as soon as spiking neural network comes in, you can mimic different synaptic properties. You can specify delays, because further the neurons are, more time it takes for a spike to go from one point to another point, right? So there are delays that are there. There are other stuff which would be something like, of course, weight is there, so the thickness of that particular thing. There are excitable connections, inhibitory connections, so there are connections which can inhibit the kind of behavior of the neuron it connects to, and those kinds of things. So it provides a lot of flexibility across that particular.
What is the thickness mathematically?
So thickness is basically weight. So more weight you have, you can think of it kind of becoming more and more open and allowing data to come in, like in a way. So thickness is basically the kind of weight of the connection that is there, because you kind of always do a convolution of kind of weight and input, right? Yeah.
Yeah. So in the earlier one that you showed, which is regarding the structure of the brain, do you also try to look at the density of the neurons within each section as well?
Yes, that's one other. So more dense the neurons are, there is an effect of data propagation based on the density as well, because you're kind of propagating into the neighborhood. That's one property that's already there, exists.
No, because I'm asking because if you look at the biological makeup of our body, the certain parts of our brain are very dense in neurons.
Yeah.
Other parts are not that dense.
True.
So what do you generally see the effect of that? Not for now, but later on.
There's a lot of heterogeneity in the brain, not only in terms of density of stuff, but there are different parts of the brain that learns differently.
Yeah.
There are different parts of the brain that kind of has different neurons. So like a brain can have like 20 different kinds of neurons which kind of interacts with kind of each other. So anyway, that kind of goes towards a lot of biophysical behavior. We are trying to mimic the biophysics of a human brain. If you have already seen the Baby X project, so Baby X simulates a spiking neural network inside the baby's head, right? So any kind of emotion goes in, kind of fires stuff, and those kind of things happen. So that part of it is mimicking the biophysical nature of the brain, and there is this strand where you are trying to implement spiking neural networks in a real engineering application. So there are these two pieces that are there, which needs to be worked on as well. A bit on learning, which is the other interesting part for any kind of neural network. So typically, if you see deep neural networks, learning is, like majority of the cases, when you have supervised learning, you have backpropagation, right? So you have backpropagation. There's derivatives that needs to be calculated, and things are backpropagated, and you kind of live in a very continuous environment, and that's the reason why you have that capability. You can calculate derivatives because it's continuous, right? So with spiking neural networks, that is an issue, right? Because you sit in a very discrete environment, and if I want to minimize some kind of function that, like loss function, there is a limitation to backpropagation. So until now, what we have seen is that most of the research is focused towards doing unsupervised stuff than supervised stuff. It's not that there has not been any supervised stuff, but there has been limitations to what people have achieved into it. In terms of unsupervised learning, one very prominent learning mechanism is spike time dependent plasticity, which is basically implements things like neurons that fire together, right? So when you have synchronous firing across the neuron, generally it is assumed that it's causal. So, like if a presynaptic spike causes a postsynaptic spike, then the weight is going to be increased. If a postsynaptic spike comes before a presynaptic spike, the weight is going to be decreased. So you kind of see that kind of a behavior for the learning. It's very Hebbian in nature. So Hebbian is basically your time asynchronous learning in that way. Right. So I can give you an example of that kind of a behavior which you can mimic in right. Let me see. Right, okay. This might work.
I think the glass is messing with you.
Right. Yeah, I could see it somewhere. Right, there you are. Alright, so I will just, I have, there's a script that we have written, this is a script that one of the Pine developers have written, which is basically a simulation of, you have a single neuron which is connected to 60 different neurons. So there are 60 presynaptic neurons which connects to one postsynaptic neuron, and then it has simulated the learning mechanism of STDP on it. So I will just run this and I will show you what happens there.
What is the STDP stands for?
Oh, that's spike time dependent plasticity. That's basically what is your asynchronous Hebbian learning, which is very unsupervised in nature in that way.
How do you start? I'm assuming you have to initialize connections that.
Yes. So
Is it just
all
random?
those are written inside. So you kind of have, yeah.
Random
So
though?
there are different ways to do that. If you are doing unsupervised learning, there's no point of doing a random initialization because it's not going towards one particular minimum as such, right? You can do a constant initialization as well if you want. Very small constant initialization is possible as well, but you can do random initialization as well. But what happens is that in an unsupervised scenario, the initial random weight provides bias to some parts of the network, right? Right. Okay. I will.
So what's post and presynaptic?
So post and presynaptic is you can think of a connection. There is a neuron, left to the connection and a neuron right of the connection where the information flows from left to right. So this is presynaptic, this is postsynaptic, and this is a synapse in the middle, right? So that's kind of one of the right. Okay. So the first plot is basically there are 60 input neurons where each neuron, you see these are the 60 input neurons which fires at certain point in time. So the 60th neuron fired at this point, this point, this point, this point, this point, whereas the 0th neuron has fired at this point, this point, this point, right? And this plot shows you how the postsynaptic neuron output the information. So you can see the kind of postsynaptic neuron has fired as these points, and while it was learning it, the weights of the neurons has got updated in some way. I'm not going into how much and so on. So you see every time things has fired, the neurons has, the connections has basically updated itself, right? And this basically shows the plot that I had shown you already. That's good. So I would now go into the second part, which is
What's your y-axis?
so y-axes are different for different ones.
Yeah, that's another one. Is that
This one?
yeah.
This one is the weight,
Okay.
right? The kind of weight is changing over time, right? So every time there is a spike, so every time there is a spike, you see that there is a weight update that has occurred, right? So every time a spike happens, the weight gets updated in some way or the other. Yeah.
how do we update the weight in this way when there is a spike?
Which spike? I'm sorry.
In the diagram in the center of this this ring, in the upper diagram there is a spike.
Yes.
And when we found a spike, how does the weight update it?
Oh, so the event is updated based on the input data that is coming in. So like when you see a spike,
Yeah.
so that is because that time that the kind of data density that was coming in was in a certain way that made it spike, because that's basically what the activation of that particular neuron is, right? So like essentially the input data drives when it's going to spike.
But in the traditional neural network, there is a back propagation.
Yes.
So we can update the parameters according to the loss function.
Exactly.
But how we change our weights or change our parameters in spike networks?
I will show you an example of how weight changes affects things in an unsupervised way. I mean, like when I show you an example, so I will come to that particular part.
I have another question. Yeah. So we have 13 hyperparameters
Yes.
of each neuron.
Yes.
We have 60 neurons.
Yep.
So basically we have 78 hyperparameters.
Okay.
How to choose the correct set or the more appropriate set of hyperparameters?
If you ask me from a data science perspective, I should say that you do a hyperparameter search. But since things becomes parameter heavy, it is a problem that exists in spiking neural network, that things are extremely parameter heavy and you have to do an automated hyperparameter search. You can do a grid search, or you can do something like a genetic algorithm which automatically chooses the hyperparameter. But one more problem is that it does not have kind of a loss function to optimize necessarily.
But the hyperparameter space is so large, we cannot run effectively on the current parameter search methods.
And that's the reason why when we were doing the research, we tried to minimize the parameters. And you kind of like, while I was doing my research, like one of my goals was to basically see what are the relationships between these parameters and try to minimize the number of parameters that you expose to a user, right? So you may see that like a change of one particular like hyperparameter correlates extremely with another hyperparameter. So you just don't need to change both of them. You can keep one constant and change one other stuff. So one of my personal research was trying to minimize the amount of hyperparameters you expose to people. I mean, like, so that it just does not, you kind of have a control over the amount of hyperparameters that you have. I will show you an example of NewCube where from all these hyperparameters, we kind of came down to probably 4 hyperparameters for learning this kind of thing. So that is where research is focused a lot as well, because biophysical stuff are extremely parameter heavy in that way. Right. Oh. Okay, now let's come to the second part of this thing, top-down approach, right? So you have a problem and then you want to create a spiking neural network system that answers some sort of question, right? Here's where I find a comparison very useful in terms of deep neural network, where many of you have already possibly seen this particular diagram, where any machine learning problem, you start, like as a data scientist, you basically start with one of these situations. I'll tell you what these situations is. One particular situation, this is the simplest situation, where you have a static input and you have a static output, and you want to build a system for that particular input output. So you have a handwritten image of a handwritten digit, you want to recognize what the digit is, right? So that's, you have a very static kind of an input and you have a very static kind of an output. The second thing is a one-to-many kind of a mapping, which is basically something like you have you have an image, right, and you want to get that, like a caption of that particular image or kind of description of that particular image, right? So what goes in is very static in nature, but what comes out is sequential, right? So so image to caption kind of a situation. There is this many-to-one situation where you can think of it reverse. Given a particular description, draw an image for me, right? That's one particular situation. You have a many-to-many situation where the outputs are time shifted. That's an example of something like a language translation. So while you are writing a particular language in Google Translate, I mean, like within a couple of seconds, it kind of starts to translate things, right? So the input that goes in is kind of sequential in nature. The output that comes out is sequential in nature, but they're time shifted. There is this last kind of stuff, which is many-to-many, but not necessarily time shifted. A parsing of a document would be that kind of an example. So you kind of read line by line and you are trying to put a page break or some sort of break into it. So like every time you read a line, you need to give a 0 or 1. That kind of a situation, right? So that's how you kind of start machine learning problem. I mean, a definition of a machine learning problem into one of these categories in general. I mean, in the last, like before the deep learning came out, people used to just solve this part, but not necessarily go into this part because of the capabilities that were there. So at this point in time, spiking neural networks can typically handle a one-to-one kind of a problem and a many-to-one kind of a problem, and not necessarily one-to-many, many-to-many. I have not seen any kind of research where you have like one-to-many and many-to-many kind of a situation. You have like one-to-one or many-to-one kind of a situation. So that's fine, right? So you have a problem and then you categorize it into one of them. When it comes to designing a spiking neural network, it basically gets into a paradigm called a reservoir computing paradigm, which is slightly different to your traditional deep neural network sense. What happens is that there are 3 layers basically. One layer is your input layer, one layer is your output layer, and in the middle sits those meshes of neurons that I was talking about. So you have a mesh of neuron which sits in the middle, which does some kind of things which I'll come to, and that transforms things into whatever you want to output, right? One very important aspect of this particular mesh is that a lot of people use it for transformation. So converting lower dimensional space into a high dimensional space. There is a definite advantage to transform data from a lower dimensional space to a high dimensional space. What happens is that things that are not separable in a lower dimensional space are generally separable in the high dimensional space. I'll show you an example. So I'll come to new cube. So here is an example. You can see this data. If I want to separate this data with kind of some sort of, like, I can either do one thing, that I create a neural network which non-linearly creates a round around it, or the second option is, which SVM also does, which is push this data up into a high dimensional space. So what happens is that you will see there's a linear separability in the 3-dimensional space. So this data gets projected into a high dimensional space. New cube, basically the kind of philosophy of new cube is to move from those biological simulation to this kind of a framework where you have data, you have a particular problem to solve, you know that it's either like one-to-one or many-to-one, and then you can just basically get the data, push it in, do hyperparameter search, and get the answer in that way, right? So in a way, the architecture of new cube is like this. So like there are 3 basic layers. So the first layer is an encoding layer. So typically, engineering data are continuous in nature, and that needs to be transformed into some sort of spike representation for it to work with spiking neural network, right? So there is this encoding layer which transforms a continuous data into these spike data, right? Then there is this second layer which we were talking about a lot previously, which is that kind of mesh of neuron. The whole idea of that particular, this particular layer of SNNC is to transform the data from a lower dimensional space to a higher dimensional space, with an assumption that at the higher dimensional space you can use a very simple classifier to discriminate things, right? And then there is this supervised readout layer, which basically does the classification or regression or whatever, that kind of thing that you can do. I'll show you this exact process in Cube. So here's the interface of it. So one example of a problem specification that we have kind of default data in that respect is wrist movement. So you have, like, while you move your wrist, we have captured EEG data while someone was moving the wrist up, down, and so it's kind of a 3-class classification problem where you are sitting in kind of a many to one kind of an environment, because over time you have data which is kind of temporal, and thing is each of your temporal data needs to be classified into one of the 3 categories, right? So I can. So what happens is load. No. Load the data, this default data that comes to YouTube. Where is it? I start this thing. Let me restart this thing.
I think there's too many open.
Yeah. There it goes. So I will just load data for classification, which you can't see at the moment, but there is a problem during demonstration. Suppose, right? Right, okay, so the data got loaded. So the first thing that I need to do is like encode the data into spikes, right? There are, I need to push it there, so there are multiple different algorithms that exist with which you can transform your data in some way or the other, and you see that there are 3 parameters right now for doing it, and like there are also hyperparameter search module through which you can optimize these things. So your continuous data gets transformed into some sort of discrete space. You need to initialize the cube. So when you, like as I told you that you can specify custom structure of your, of your spiking neuron layer, right? So we'll, for example, we will create a custom structure. Your custom structure, and then also the input structure.
What are these structures?
Sorry?
What are these structures?
Oh, the structure is that at what point in the space input goes in.
like placeholder intensity.
Right, right. I mean, these things can be automatically searched as well, by the way. So I specify where the input goes in, which is the mapping of the neuron. And now I need to train the cube, which is again, you see now we have come down to 6 different parameters that you can choose from let's say, 50 different parameters, just by kind of like figuring out what are the correlating parameters, and we don't need to worry about it, or it does not affect much on how kind of things behave. I'll keep it default, and it's running. This has learned it, and you can see how things has been simulated. So you see things starts firing, and parts of the network now starts firing, and you see it will kind of increase, decrease, and it kind of behaves like what you call, like I remember someone saying that it's like, so someone said that it's like throwing a pebble in a pond. So you basically push some input in, and so it acts as throwing a pebble inside a pond, and it kind of creates ripples around it, right? So that's the kind of behavior that you are seeing over here. So I will stop doing this.
How many neurons do you have?
In this case, probably
1,485. And 14 of those are input neurons, which are the yellow bits.
Oh, these are input neurons.
Yep.
Did you
Right,
count
so
them? How did you know that?
Oh, that was driven by how EEG electrodes are placed in the brain, right? So EEG electrodes are placed in the brain in these locations. So we kind of try and mimic that
For
kind
the
of
inputs.
behavior in that.
For the inputs.
Yes.
Okay.
Yeah. And thing is, this particular positioning of the neurons are driven by actual brain neuron positioning kind of a thing, even though like highly compressed in that way. But thing is, it's driven by those kind of things. And now there's the third layer of things, which is training the classifier. And if you train it, it basically sends the spikes and stuff into this third layer. There's something that's wrong.
So you can't actually make predictions directly from the neuron's activity?
No, because the kind of middle layer is unsupervised, right? So if you are trying to discriminate things, you have to discriminate things with an unsupervised way. The whole idea about this middle layer is to transform the data into a high dimensional space so that things can be discriminated pretty easily. That's the whole idea. I mean, that's the same idea SVM also works on. SVM basically transforms the data into the higher dimensional space because inherently SVMs are linearly for linearly separable problems, right? So if you have non-linearity, how do we deal with it? Instead of trying to learn a linear function, you transform it into a high dimensional space where you can separate things with a linear hyperplane, right? So that's a kind of an idea.
So what's the transform function from low dimension to high dimension?
So that's
such as the kernel function.
Yes, that's the kernel functions are basically the differential equations which actually drives the kernel transformation, right? So those are the internal lower level detail that I was showing you earlier as the properties of the neurons that kind of drives the kernel functionality of that kind of thing, right?
How does the shape of the, the arrangement of the neuron, how does that affect the performance of the model?
So the arrangement, so rather than the arrangement of the neurons, the model is being affected generally by the number of connections more than the arrangement or the number of neurons. You can think that if you do an all by all connections, it goes up by square, right? So you have a squared number of connection. So scalability is generally driven by the connectivity. That's one of the reasons why you have partially connected stuff. And there is one more thing that drives it, is the spiking activity. So the rate of the spiking drives how much computation that kind of needs to be done in terms of, I mean, like what kind of processing that kind of needs to be done.
Because before I saw that brain-shaped one, and then here is a more spherical one. Just wondering if there's any difference between like a, say, like a cube one versus a spherical one.
If it is the similar number of neurons, it wouldn't affect the scalability as much. Like it would take like similar kind of time. The only thing that are different are delays if you kind of stretch or kind of compress stuff, right?
Can you maybe show the connections? Just
Oh, that's fancy, right?
yeah, and then use the 3D wiggly thing to just show it from different perspectives. Just to, I don't know.
So just to quickly clarify before you do that, so you take those outputs as effectively the values coming out of those 14 things,
Those are spikes,
and then put them into a logistic regression.
not logistic regression. There are supervised, spiking stuff that is there as well, but this can be k-nearest neighbor, it can be logistic regression, it can be anything as such. Okay, what Anne was saying that because of the spatial arrangement of stuff, you can do a lot of graph analysis, right? So you can go into network analysis, and there are many different ways to kind of see how things have interacted and so on. So I am not going into the detail of these things, but maybe I can show one example, which is this one. So this tells you with the input neuron how much interaction or kind of spike activities has gone, communicated between the feature 5 and feature 2, like one of the two electrodes, so it's kind of thicker interaction between them. So there is a level of interpretability that is attached to this kind of spatial arrangement of stuff, and you can do graph analysis like on these to basically gain some sort of insight on what causes what kind of behavior and those sort of things. There's this separate network analysis tool that's already there, and there are a lot of documentation on what means what and how you should interpret those. Okay.
So maybe stupid question, but which neurons are the outputs?
So the output neurons are all the neurons acts as output. That's why we are saying transforming to a high dimensional space, right? So your input, number of input neurons, there were 14 input neurons, 14 input neurons there, whereas the number of output neurons where you are getting the spikes are how many? Like 1,400 something plus 14, right? So it has transformed it from a lower dimensional feature space to a higher dimensional feature space, and it uses that kind of piece. Yeah.
I saw in the previous page diagram there are 13 features. 13 features in the previous diagram.
Oh.
13 features. How to choose the 13 features?
Those features are the data that you have, basically. So you can think of, you have, so like in this case, we had EEG data, right? So we had a 14-channel EEG data set where data gets generated for 14 different points of your brain, and those 14 points becomes your input, right? It's kind of very similar to your traditional sense. If you have data which is sequential in nature, and you have multi-dimensional data, right? So you kind of have multiple features, and each feature has, are kind of temporarily getting extracted.
The 13 features are the inputs.
Yes, exactly.
How many connections between the neurons?
Oh, it's being driven by a particular algorithm called small world connectivity. So you can read about small world connectivity. It basically says that connect with a certain amount of probability within a particular neighborhood. So every neuron, with a particular probability gets connected to the neighborhood, and as you go further away, the probability reduces, right? That's one way to do that. There are many other ways to connect stuff.
You mean the connection between the neurons can disappear?
Oh, yes.
In
Through learning.
In some situations.
Through learning, as soon as the weight becomes 0, there is a probability of that being disappearing as well, right? So I probably did not show you the connection.
do neurons themselves have the ability to die?
Not without learning. Not without learning.
No, like, so if the neuron becomes fully disconnected, and therefore will never be able to.
Oh, you can potentially do that, not in this particular implementation,
So you
but
can
it's kind of
program it.
possible. Yeah.
Because that probably would happen in real life.
Yes. You can do that. Like it's not implemented here, right? So, but that can be implemented. That particular.
It's probably not relevant yet because the scale of these things is significantly too small. But like in the brain, as far as I'm aware, and I'm not a neuroscience by any means, there is kind of large cross-region connections as well that happen due to other effects where you get sort of very distant connections also able to occur.
And you can do that as well. So, I mean, with certain probability, you can do a long-distance connections, right? Like which is basically like I think of it like exploration and like exploitation. So you're exploring your existing neighborhood, but I mean, in a genetic algorithm sense, it's kind of a mutation operation, which basically allows you to do long distance stuff so that you kind of, there's some sort of causal relationship that can exist in a kind of long distance as well.
In your neural model, you had a number of parameters that you can actually play around or change it. In your result, like this result, this example, if you change those parameters, how sensitive the output is?
It is sensitive.
Relates to this.
Not. I won't say it's really sensitive. I mean, like, it will depend on how you implement stuff, and it like depends on the internal implementation of stuff. But there are some parameters for which it's extremely sensitive. For example, if you are changing something like a threshold potential, which is here, which is extremely sensitive to the kind of firing rate. So if you reduce the threshold potential, things will fire more often, right? So that behavior is being driven by the property of the neuron, and I mean, just by doing the research, I know there are some that are already existing, but just looking at it, you can't, I mean, discriminate. You can figure it out in the results, and that's the reason why you do hyperparameter search. You have to do hyperparameter search. But there is I mean, like sensitivities are part of this thing, right? So it just has a landscape where things can be quite sensitive for certain kind of parameters. All right. I will straight away, because probably we're way over time, right? No? Okay, so I will show you one other example, just last example of doing the handwritten digit recognition using very like famous MNIST data set where you have 9 different digits and have images for those digits, and the idea is to recognize the digit for that particular data set. So
I have had advice that we need to be gone by 8:30. So we've had some pretty good Q&A throughout this, which is awesome. So maybe just limit your expectations about like how big the QA session is at the end, and we should be fine.
Right. This is one other very nice work I have found where someone tried to solve very real life digit recognition problem, even though this is a one-to-one problem, by the way, not a many-to-one problem. So it's not as complicated in that way, but people are very excited about computer vision, right? And you can solve everything. So that's a good application. And why I got a bit excited about looking at this was that the system could achieve around 95% accuracy without using any kind of supervision. So there's no supervision done, right? So it totally solved an unsupervised learning problem and still achieved 95% accuracy. And if you have been hearing what where AI is moving towards finally is like where the people say the kind of cherry of the cake is where unsupervised learning, because you have like such a massive requirement of data when you like have to do kind of supervised learning kind of environment, right? Some like important aspect that I liked about it is this thing, and if like one other advantage which I did not touch on at all, if you can create systems like this, it's going to be extremely power efficient, because you see it works on spikes. So you essentially compress the data you not only minimize your amount of data that needs to be processed, but if you think about computing systems from floating point operations, you are kind of going into your traditional fixed point operations, right? And that that essentially means you're kind of minimizing the computation cost in that.
What about the amount of data you need for classification? Do you need a huge amount of data, basically?
This is a very open question. This is a very, very open question. So typically, I would say you would require less amount. So things that spiking neural networks can learn well, you would require less amount of data to learn it than your supervised learning. Scenario, because of the nature of things that drives it. So I was using Brian, so you can totally download the GitHub repository and kind of run it. So I have put the GitHub repository into it. So before I go into the spiking, how this solved using spiking neural networks, I will basically explain you in your traditional neural network environment where things are static, how you do it, and then transform it, because it's much easier to understand it in a static environment and then move into. So how they solve it is, many of you will already know, self-organizing maps. So self-organizing maps are basically feature transformation, and it's called competitive learning, where neurons basically compete with each other to win, right? And it mimics the behavior of k-mean and that kind of a stuff, but additionally there are competitive stuff. So if we try to focus on the architecture, a self-organizing map architecture is two-layered architecture. You have a set of input neurons. In this case, the input neurons are intensities of the pixels for a particular image, right? So you have a digit where 28 by 28 pixel space, which so 784 input space. So that's your input space, right? And on the next layer, it basically creates a grid. Again, you see that there is a spatial component that is attached to it. So there is a spatial grid that sits there. On top, right? And let's say you input the data, continuously input the data and learn it. What you will see at the end is something like this, where, I don't know if everyone can see it, the colors basically represents the image of a particular category of digits. So for example, 6 is this one. The yellow one is 6, and you will see that 5 is very near to 6, because 5 looks quite similar to 6. Another interesting thing is that 5 is quite similar to 8. That's the reason why there are some images which looks very much like 8, and that's why they're clustered in that particular space. The way this particular algorithm works is you initialize the neuron at the top layer with random instantiation of image intensities. So think about random 28 by 28 images sitting over here, right? As you push the data, it calculates some kind of similarities for all of those, and the one that's closest to your input data wins. So there is this winning behavior. So let's say here there is one particular neuron which is, so your input is digit 7, image of digit 7, and here is a neuron where, where the neuron was initialized with a particular image intensity where it was quite similar to 7. So what will happen is that, when you measure similarity, this thing will win. And as soon as this thing wins, what it does is that it also propagates the winning behavior in the neighborhood. So this kind of cluster starts forming, right? What the spiking neural network architecture for, which is very similar to the self-organizing map architecture, is that they mimic the self-organizing map kind of a behavior with two different grids, where there are excitatory neurons sitting here and there are a bunch of inhibitory neuron that sits here. What they do is that they have this input thing. There is an all-by-all connection, same as self-organizing map. So one of them wins, and when it wins, it pushes the information to the inhibitory neuron and it inhibits everything else. So what happens is that the kind of proximity of one particular type of thing going towards one particular space increases. and that's basically how they mimic this particular behavior. I'm not going into too much detail into the thing. You can totally read the article if you want, but that's extremely well done, mimicking the behavior of self-organizing maps, but not necessarily exactly a self-organizing map. So it kind of sits in a temporal environment, and so on. Other than that, so that's basically their accuracy. They show that as you increase the size of the grid, so as you increase the number of hidden neurons in a way, your performance goes up. And this is the interesting part. You will see that it actually achieves like around 95% test accuracy, test performance, using like a very unsupervised STDP kind of a framework. And there are many other kind of hybrid of deep neuron in a way. So they use restricted Boltzmann machines, and they kind of attach spiking properties to it. This is my last slide. So coming back to deep learning versus spiking.
So can you just maybe very briefly touch on how the pixel intensity would be modulated into spiking?
Oh yes, that's something that I did not specify. But what you do is that you can very easily, so the easiest thing to do is pixel intensity. So as the pixel intensity goes higher, the spike rate goes higher. Right? That's one way of doing it. There's one other way where, which is extremely efficient. That's more the pixel intensity, earlier it spikes. So you will have, so higher value leads to a insertion of spike earlier, right? That's kind of thing that you can do. There are like other ways of doing those as well.
So you sort of divide each like one cycle in the frequency would be divided into
Yes.
like 256 possible times to spike.
Absolutely, that kind of a thing. So you can do like a single stuff, and you can also do rate. So there are different reasons why you want to do one or the other. So there are this rate coding and temporal encoding, which I'm not going into. Temporal encodings are typically very efficient, but we do not know much about how brain does temporal encoding. That's one problem. But if you can do temporal encoding, it just represents information by the timing of the spike rather than the actual spike. So the representation is extremely efficient. Whereas rate coding is basically transforming your intensity value into spike rates, right? So a single spike is not important, but when you do like aggregation across many spikes.
Does it matter to know how the brain works, or you can just test different approaches and see which one is the best?
That's the data science approach. So where you can test all these kind of scenarios and like figure out what neurobiologists will say that do things with. This is one aspect I always thought about when I did my PhD. That is, what should I build? Should I really concentrate on the biophysical aspect of it, or really take the inspiration from biophysics, which makes sense with respect to data, right? I should be, so something,
what should be loyal to the biophysical biomodel of the model, the aspect? What's the benefit of being loyal to the biological?
Well, the thing is, these two fields have actually diverged a lot from the point that it actually started off with. When deep neural network came out, because it could actually figure out some sort of hierarchical flow or hierarchical learning that takes place in certain part of the, of our brain. It took that particular inspiration and converted it into a kind of mathematical formalization, so that it kind of makes sense in terms of data. So one does not need to be specifically loyal to the biophysical aspect of things if it does not make sense in terms of data. But if it does, and some of it does make sense. For example, the transformation in terms of intensity to a single timing of the spike is one aspect. I would say, it makes perfect sense in that way, right? So you have just one data point to kind of represent a high value. You have the exact same data point to represent a very low value, but it just, when it gets. Well, most of you must have already read it.
I guess for the deeper neural network, the data representation must be discrete.
For deep neural network,
Yeah.
typically the data representation is non-discrete, right? You have continuous data going
It
in.
must be discrete because if it is continuous data, we should separate it with different segments and use one hot coding to integrate
Yes.
encoding.
Yes, true, right.
So the data representation is discrete. But I think for Spark neural networks, the data representation can be continuous.
Oh, you can do continuous data representation, but not necessarily the whole ecosystem works inside a continuous data representation, right? Because spikes goes in, spikes comes out. You can represent it as a continuous function in a way because you can kind of give all zeros and one, then goes to 0 and 1. But thing is, inherently they are discrete. There's nothing in between 0 and 1 that contributes to the activation of things, right? That's basically the idea, right? I mean, you can very easily think about how is a spiking neuron different from something like a step activation neuron. In step activation neuron, your output is discrete, right? It's either 0 or 1. But if you think about the input, that's continuous, right? But in case of spiking, both of them are discrete in that way. In terms of process, I mean, some of the things that I just go through, which is part assumption, like I have already discussed about it, which is high because you have a lot of floating point operations going on. Process is not that noisy, and spiking is noisy because the reason why I say that is you can't, if you are living in a rate coding environment, you can't do anything with respect to one spike, but you have to approximate across many spikes. So there can be noise that can be attached to this thing. Learning, deep learning is typically in a supervised framework. It's error minimization by back propagation, whereas spiking is very plasticity driven. When it comes to the efforts that you need to do in terms of learning, deep neural network is extremely parameter heavy, computation heavy, slow, but in terms of training, not necessarily prediction. Spiking is also extremely parameter heavy. It is also computation heavy, but typically, because it's unsupervised, it's one pass rather than many pass. So that's one, like, this still might be apples and oranges, but thing is, that's the way, I mean, like you can put it in that way. So one thing I have noticed which is really important is problem formalization and application building efforts are generally low, so you can basically choose, so I have a problem, I need to answer a particular question. First thing that I do is that I put it into one of those 5 frameworks, then I build the architecture, I learn it. Whereas when it comes to spiking neural network, you need to also figure out what those parameters are. So the kind of amount of effort that you are doing is slightly higher in that way, right? But the way the research is progressing, today I actually saw an Uber post which basically says that they have already invested a lot of time and they have come very close to building differentiable plasticity, which tells me that things have moved in that way. There are a lot of investment going on in IBM. IBM True North is one of the spiking neural network hardwares that exists. So IBM has True North. There are Steve Forward from Intel is investing heavily on spiking neural network hardware. So you can see once you convert this into a hardware environment, hardware will give a very natural parallelism. And if you can create those kind of architecture where you move from a typical von Neumann kind of a scenario to a rather stochastic hardwares, there's a massive push towards that because Moore's law is not going to stay forever, right? So, I mean, like, the thing is, von Neumann architectures are typically very sequential, right? Whereas these kinds of hardware architectures are inherently parallelized, right? I mean, von Neumann architectures, you can do parallelism, but you kind of do on top of something being really sequential. But thing is, your this kind of a hardware would also become at one point in time extremely capable in terms of what can be done, because it will do stochastically. Okay, let's not go there anymore. Okay, so I am happy to answer any other questions that you have, and that would be kind of what I could.
Find the microphone so we can pass it around to whoever that's asking a question. I wonder if that one's dead.
You tap, just
No, it's
use,
working.
tap.
Hello.
There you go.
Hello. Okay. It's blinking red at me. Cool. We had a hand go up over here. Yep.
In terms of performance, do you need as well GPUs and large clusters to train and to do all the kind of things? If you start to become heavy in terms of neural spiking.
Me and Anne did a work where we could simulate how many, around 200,000 neurons?
241,606.
Like within a kind of 4 gigs of memory and kind of your typical commodity hardware. That very much depend on, lot of it depends on the data representation, how efficiently you can create those data structures, that we could really optimize the data structure and move from squared scalability to a very kind of linear log kind of scalability. So, I mean, there are performance aspects that are there, but you can work with it. There is nothing wrong in that respect.
Cool. So we a little news item, actually, or big news item that I was very negligent in saying this evening is that Anne has joined our meetup organizer team. So yeah, we're for obvious reasons very excited about that. And yeah, I just wanted to. Is this still going?
I don't think so.
No,
We can
yeah.
hear you.
I think it's low on batteries. I'll get the other one.
Sorry, it's not just for me, it's for the recording, for those folks who can't be here tonight. But just on that performance note, Neil, you mentioned it was one-pass training. Does that include the sort of machine learning second phase that comes after you've got the weights?
So you do the one-pass learning to update the weights, right? And thing is, because you do one-pass learning, there is this also, I mean, like one other aspect where you can literally have a lifelong learning kind of a scenario as data comes in. For example, if you sit in your very traditional supervised learning environment, you have massive amount of data that goes into the training, the model comes out, and then another massive amount of data needs to come in for it to learn again, right? Whereas in this kind of a scenario, I mean, Uber was mentioning it today in that respect. So, I mean, like it was really interesting how they have seen this particular problem where they're thinking that you can literally fire up a particular neural network and it just learns lifelong over time as data comes in, and you kind of don't have to worry about retraining or updating your stuff over time, like because it's so kind of simple one-pass kind of stuff that's there.
Naturally online algorithm.
Yes, true.
I guess it's very pretty much the same question, just in a slightly different wording. So typical neural nets, obviously, the main thing that's kind of exploited in recent years is GPUs and things like that. And I'd say part of that is because of how easy it is to take that mentality of matrix stuff to GPUs. This doesn't seem to have any of that.
No.
Is that an insurmountable barrier to this being used?
Yes, there's a barrier to using this kind of thing because it's asynchronous. So the spikes that interact with each other. So I mean, like, why you can transform your stuff into GPUs, because things are typically, you have matrices and you can do a direct product of stuff and it just gets you results. So, but when it comes to spiking neural networks, because the spikes are asynchronous in nature and the computation is not really a straightforward matrix multiplication or that kind of a thing. So straight away, you cannot just push things into GPU to do part of the computation.
Have you tried doing, have you tried utilizing any of the like GPU accelerated stuff to actually?
We have not tried using GPUs, but we have tried using one of the spiking neural network hardware,
Okay.
where you can simulate
Like
things.
an ASIC or something.
Yeah, it is. Yeah. So we got that hardware from the University of Manchester, who gives you the capability to run spiking neural networks on top of their hardware straight away, right? And you can achieve massive amount of parallelism in that respect, right? That's not my research topic. Not my kind of expertise as well. So I won't be able to go much deeper into it. But those kinds of things has been done in some way.
I've got one more question now for this, which is, so it seems like it's needlessly, insanely complicated, the internal functions. Like, how simple can you get and how much do you lose? So like, why not just the most basic differentiable function you can imagine, and just using those? Have you tried like just removing all those crazy parameters and just...
Yes, that's what we have tried to do. So you kind of remove all those crazy parameters, keep it to constant, and use the parameters that affects the performance the maximum, right? So that's up. The thing is, I have found until 2010 or something, all the efforts in spiking neural networks was focused on biophysical simulation, rather than trying to solve data problems with it. And I feel NewCube kind of, from a philosophy perspective, I feel that it actually captured that particular philosophy. So you have data, you have a particular thing, like some sort of problem formalization, and you can run a bunch of steps and you kind of get your results, right? Which is something that was lacking quite a lot in that way, in terms of like solving data problems with respect to using spiking neural networks. And things are pushing forward very fast in that way.
Maybe someone down the back? No?
I have more questions.
Anyone? No, I don't. You've already had all answers through the talk.
I've got a few. Okay, my first question is, how do inhibitory neurons play into the MINTS example? So I didn't quite understand the structure there. If it really isn't something you've looked into, don't try to answer that.
To put it really simply, so excitatory neurons excite, so once it releases spike, it excites the vicinity around it, right?
Yeah.
Whereas an inhibitory neuron, the kind of spikes that it kind of broadcasts, it inhibits the potential of the neurons that are like around it. So inhibition and excitation can be a property of a neuron, it can be a property of the connection as well.
But how do you decide which, like...
That's the thing, right? So that's part of an optimization problem, right? You can think of it as a hyperparameter, right? That's how you define deep neural network architecture, is by doing like different kinds of things, right? That's kind of an architecture question, that how do I architect so that I make sure that the problem that I'm trying to solve is learned maximally in that way, right? So there's no clear answer to that in that way, and yeah.
Yeah, I'm sure it's something I have to read.
Yeah.
I've got one more question as well. If anyone else want before I... Yep.
Sorry, I might have missed this, but you had a new, the new Cube application? Is that available for download, or?
So it is available for download. So right now you get, so like there is a license, but generally there's a demo version which you can download, play around with, and do things around it. But for the full version or something, there's some sort of licensing that's there. You can contact AUT, you can contact Kedri for that kind of
Right behind you there.
Have you explored evolutionary algorithms to minimize the number of parameters that you have to learn, so they learn within generations?
Some work was going on in terms of using evolutionary algorithm to keep that network to a stable state. So as soon as you achieve kind of hyperstability, so things starts firing a lot, is not a good behavior. So there was some sort of optimization that was done to keep it in a kind of subsaturated state, space. But and thing is, evolutionary algorithms can be used to do hyperparameter search, which is already implemented. So you can do hyperparameter search using evolutionary encoding. So which I mean, like, it's already part of NewCube. So if you go into the hyperparameter search, I don't know, button, you will see the option of using evolutionary algorithm to do the hyperparameter search. So yeah.
I can speak without the microphone.
Oh, it's just for the video, if you don't mind, I'll get you the big question. But just because it's part of another question, if you don't mind, just briefly, you said that the inhibitors and the exciters affected the neurons around them, but isn't there only a single output synapse per neuron?
No, I mean, like, when you create a network from a presynaptic neuron, there can be many connections that can go out to like many others. So the spike can be broadcasted to many other places of the network.
So multiple inputs and outputs?
Yes, yes.
Is there a prune to stop loops into itself?
So thing is, the internal implementation does not allow, I mean, that's why I say a cyclic graph. So
I mean, there are actual cycles.
It will not loop into itself.
But wouldn't you want cycles sometimes?
I have not found a situation where I want cycles, but if you want cycles, you can. It just
But that'd be too desirable, obviously. So
oh, yeah.
That's possible,
Yeah.
Sure. How does the human brain solve that?
So the human brain does not loop to itself, as far as I understand. I'm not an expert in that, by the way, but thing is, I would not expect my brain cells to be looping to itself.
On the short term, but in a really long term.
Maybe. I mean, I have no idea. I would have no idea.
I have more general questions about neural networks. Imagine you have to build a classifier, image classifier, to differentiate, I don't know, a cat and a dog. How do you know in advance which kind of network you will choose? Will you try different architecture and compare the accuracy, or is there a way to find out in advance what will be the accuracy?
There's no way to find out what will be the accuracy, but based on the data, I mean, because I have worked with spiking neural network for some time, I can kind of see what will not work and what will work. But that at this point in time, there's no very clear heuristic at top level that you can specify that. So there's no one clear heuristic.
There is no rule, it's more on your personal experience that you know that it will work or it will fail.
Well, I mean, my goal always is to control the spike rate. So any way with which I can control the spike rate inside the neuron will give me a good discriminable kind of space at the kind of higher dimensionality. So any parameters that massively affects the spike rate within the network is not good. And there are multiple parameters that affect the spike rate, so you have to control the parameters in such a way for the neuron that it kind of, the spike rates can be kept within a particular limit, and that generally gives you a good higher dimensional separability which can be learned. Right? That's like one heuristic that like I find is extremely useful.
My observation is that there's a lot of kind of intuition and experience when it comes to kind of finger in the air selection of our algorithms. But we had a really good talk, I think it was our second talk. If you go into a message board, there's like some historical videos and stuff. Second talk we ever had, there was a summary of which general deep learning and machine learning tools fit which problem spaces typically. So that might be useful for you.
It's changed in the past 6 months. You guys better read what status.
And some United States institute or university involved in spiking neural networks?
I didn't get your question.
What United States American university or institutes involved in spiking neural networks research?
Oh, so what's happening in US are you talking about?
Yeah,
right?
yeah.
Oh, that's what. So The IBM True North development is mostly happening in the western part of the country. So Uber sits in the US, who does a lot of work in terms of spiking neural network. Internally, there's nothing come out from them as yet except blog posts, right? So there's internally a lot of work going on with respect to a lot of different companies which kind of sits in United States. It can be IBM. There's Intel is working a lot on spiking neural network hardware. So a lot of effort I see is focused on implementing these sort of stuff into the hardware straight away, which gives them low power consumption, which is one aspect that I was talking about, which people are doing a lot of stuff. In terms of software development, as I said, like Uber is into that. IBM has some sort of software that kind of works on top of IBM True North. So there's a lot of work going on in that way as well.
Is there a go-to university in the States for this kind of research?
The go-to university for me was not in United States but in UK. So University of Manchester is doing a lot of work because Steve Ferber, who is one of the person who developed the Intel chip, sits there. And so you know about the Human Brain Project, right? So the Human Brain Project was one of the European Union project trying to understand human brain, and part of that was development of this kind of hardware chip, which Steve Ferber basically headed that particular aspect, and they have come up with this Spinnaker architecture, which is somewhat go-to for. So Pine, for example, is being developed by University of Manchester. Now it has come under Neuro Ensemble, but it was initially proposed by University of Manchester and then kind of got into.
Sorry, but about the Baby X, how much do you know about the Baby X project? Because you said it's using the spiking neural.
Some parts of it is using, because this is anecdotal, but I heard from my supervisor, Professor Kasapov, that when the Baby X project started, they had a lot of kind of interaction with respect to how this biophysical brain could be built. And when you see Mark Zager's talk nowadays, you will see those spiking properties sitting inside those kind of things. So that's one thing that tells me that it's kind of still there and kind of going on pretty well. There are other aspects that has come in, definitely. Computer vision has come in. There's speech recognition has come in, a lot of stuff has come in, but the internal brain, some of the emotions that the baby shows are being driven by spiking neural network. If that has not changed drastically.
Okay, I think we better leave it there. Let's thank Neil for very generous time. Everyone have a good night.
Yeah, thank you.